All right, so what we're going to be looking at now is that we're going to be looking at the mathematics of getting around. So we're going to be moving around, trying to do different things, and trying to see if we're able to go in a certain path or not. Okay. The little subtitle for this that I like calling it is it's kind of for this one we're stripping down to the bare bones. Okay. Not bare like animal bear, like bare bones. Okay. So we're stripping everything down to basically the essentials, the structure of the things that we are using. And that's what we're going to be doing. Okay. So the first things first. Here's your setup. You are a ghost. Okay. Ooh, a ghost. Okay. Now, the ghost council has decided to say you have to haunt this house, and what you have to do is you have to hit every single wall once and only once. Or let's see how you can do it. I don't know how you sounded, kind of like a pirate, but anyway. So here's your house. So we've got the living room, the dining room, the living room, the bedroom, the bathroom, and the kitchen. Okay. And then we've got outside, with trees and shrubbery and, other things. And so let's see if we can do this. So we're going to start out here, and we're going to go, okay, we're going to go here, 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 and it looks like I'm stuck because I've got these two here, but I can't get over there. So I didn't work that time, so now let's try another one. We'll do this one in blue. We're going to start inside this time, and we're going to go from here to here. Outside, outside. Oh, I've already done that one. Okay. So as you see, that one didn't work either. Now, we could be doing this all day, seeing, okay, if we can find one. Now, the question is there one? And if there is, what is it? And so this problem is based off another problem called the Seven Bridges of Königsberg, which was a very, I guess you could say, famous problem way back in the day. The Seven Bridges of Königsberg was in a city, and there were 7 bridges, and the question was, is there a way to walk across all 7 bridges without going over any of them twice? Okay, so it's like the setup of the one that we had with our ghosts, but it's a little bit different. And for years and years and years, people were like, well, it might be possible. Well, then they would try to find one. And then it kind of was a consensus, no, it's not possible. We can't do this. But nobody was able to prove it. And that's the big thing with math, is that you have to be able to prove the things that you're doing. And so nobody was able to say, yes, this is not possible, here is why. And it's not like who was it? Fairmont, who tried to pull off the, oh, I did this, I did prove it, but I don't have the space. I don't have the space to show it right now. Yeah, Fairmont kind of did that with his last theorem, which was finally proven by Andrew Wiles in 1994-96. But anyway, so the man that kind of took this and was like, you know what, I'm gonna do this, was probably one of the greatest mathematicians and scientists that ever lived, Euler, Leonard Euler, and he's famous for his Euler constant, this principle, and he did other things with optics and physics. He did so many different things. He's kind of got his foot in almost everything with science around the time that he was doing it. He is considered one of the greatest mathematicians to ever live. But we're going to be focusing on his work with graph theory. Graph theory, graph theory, graph theory, graph theory, graph theory. That is what our focus is what he kind of did. He kind of put graph theory into the new millennia. Okay. And so looking back at the Seven Bridges of Königsberg, Euler looked at this and said, you know what? There's a lot of garbage here that I don't need. I'm going to take this and I'm only going to put the stuff that I need of this problem. Okay? There's certain things that I don't need, and I'm going to ignore those. So like all these streets and roads and everything else, and that it's an island and that they're bridges, or that there's water, and there's a guy named Gary that lives 2 doors down. See, yeah, he's very boring. But he's like, I don't need all this. So what he did was he's like, okay, here's a stopping point, here's a stopping point, here's a stopping point, here's a stopping point. I'm going to put 4 dots to represent those 4 blots of land. Okay. After that, he said, okay, how are they connected? Well, this one is connected to the middle one by 2 and to that one. This one's connected to these 2 and that one, and this one's connected there. And he took this, and basically this is a graph. This is what he did. Was he took something that was very confusing, had a lot of different things, people were worried about the distance between them and all this garbage. And Euler was like, no, we just need to keep it simple, stupid, KISS. And so that's what he did. He broke everything down and kept it easy. Easy, easy, easy. All right, so when Euler did these graphs, what he did was we have this setup. And with a graph, there's many different things. There's a lot of terminology and different things, and hopefully you'll be reading more about this and doing a little bit more research on this. But I'll go through some of this right now. The first thing is this is called a connected graph. It's a connected graph because you can go from A to any variable or any other vertice, which is the point, without picking up your pencil. Okay, it's all connected. There's nowhere that you have to jump over, and you can go from A to any of the other vertices, and so it's a connected graph. Okay, A right here has this this circle attached to it. It's called a loop. A loop basically is you start one location and you end in the same location. Okay, it's a loop. Okay, so we call those loops. Each of these red dots are called vertices. The blue lines are called edges. Okay. So the dots are vertices, the lines are edges. This right here from D to E and E to D, okay, those are parallel edges. That means that there's 2 different routes going from D to E. Okay, you can either take route A or you can take route B as your choice. Now, the one thing with these edges is that they do not have a direction. So you could go from B to A, or you can go from A to B. It does not matter. Either direction is the same. Now, even though you see CB crosses AE, this is not a vertice. That is not a vertice. Just because they cross does not mean they're a vertice. Okay. This same graph can be drawn a different way, but it still will represent the same thing. Okay. All right, now, another big thing here is called bridges. Now, what a bridge is an edge that if you eliminate it, creates a disconnected graph. Here's a disconnected graph. EF would be considered a bridge because you disconnected the graph. Okay. When we removed it, it's a bridge, and we've created a disconnected graph. As you see, there's a couple other bridges here. GF is also a bridge, and HF is also another bridge. Okay, but now we have 2 components in a disconnected graph. Now, if we eliminate GF, now we have 3 components. We have this component, 1, we have this component, 2, and we have G all by itself, 3. So we have 3 components in a disconnected graph. Now, G, there's something special about G. G would be called an isolated variable, or an isolated vertice. It's all by itself. There's no edges attached to it. There's no other vertices. It's all by itself. It would be called an isolated vertice. And so it's kind of a special one. I mean, we won't look too much into it, but it just has a special name. Okay, but we've got 3 components here with these. Okay, now let's go back to your ghost. Okay, so you're still floating around, spooking people up. Okay, so back to being a ghost. Okay, so back to that house that you're trying to haunt. Okay, well, let's look at, okay, what are our vertices here? So what is what is our vertices? Well, our vertices in this case will be the rooms. So we have 1, 2, 3, 4, 5, but we also have another one. We also have outside, because we can go outside. Okay. Now, what would be your bridges? Or what would be your edges? Not bridges. What would be your edges? Well, your edges would be all of the walls that separate the rooms. So these are all the paths you can go from one of the vertices. Okay. So now when we draw this, okay, so I've put our dots here. Okay. This first one, this will be outside. This will be the that was the dining room. We'll say this is the living room. This is the kitchen, the bedroom, and the bathroom. Okay. So now let's draw the edges that connect all these. So from the bedroom, we had a wall going to the kitchen, to the bathroom, to the living room, dining room, and one to the outside. Okay. Now let's look at the dining room. The dining room was connected to the kitchen. It was also connected to the bedroom, but we've already drawn that one. It was connected to the living room, and it had two going outside. The living room had two going outside and to the bathroom, and then of course also to the dining room and the bedroom. And then the kitchen had two going to the outside, along with the bathroom also had two going to the outside. And so there would be our graph. Okay. Now this is going to be easier for us to identify if there is a path or not based on what we see. Okay. And so when we go a little more detail into this a little bit later, we'll be able to say, okay, yes there is, or no there's not, based on what's called Euler's theorem. Okay. And so this is just taking something that was very complex, that room with all those walls and everything, and we broke it down to something easy. We broke it down to its bare bones. Okay. We're stripping everything to just its skeleton, what we need, the structure of the problem.